Alright guys, we're going to continue Unit 8, our lesson on acids and bases. So Part 7 is all about this concept of percent dissociation. And this is what percent of your compound is breaking down of the acid, like when the H pops off the acid, what percent of your original initial amount is actually popping off to make that hydrogen ion or that proton concentration. Now, if you remember, our strong acids are going to 100% dissociate, so this is only going to be for weak acids. For strong acids, it's automatically 100%, so we're only going to have numbers to work with for weak acids. So here is our formula. Percent dissociation is amount dissociated, and that's in molarity, divided by initial concentration, and that's also in molarity, so you'll notice those two things cancel out. And these are one of those things that really irks me about formulas. It says times 100%. That's what you're going to see in every textbook, or if you look this up online. Do not use the percent button on your calculator. That'll cancel out the 100. This percent is a unit. So that's just so you know, in the end, it ends up being a percent. You do have to multiply by that 100. That is a number you're working with. But the percent sign, do not use the percent sign in the calculator. It'll totally mess up all your calculations. All right, so this is a basic percent formula, part over whole times 100. That is always the formula you use to find percent. So let's talk about hydrofluoric acid. We talked about that earlier. So if I have a 1.00 molar solution of hydrofluoric acid, we remember that that led to a hydrogen concentration, we did this earlier, of 2.7 times 10 to the negative 2 molar. So if I wanted to know the percent dissociation of HF, then that would be the amount of dissociation, or basically you can think of it as the hydrogen concentration. So 2.7 times 10 to the negative 2 molarity divided by 1.00 molarity, because that was my initial concentration of the full acid, times the 100% is just a unit, so times 100. If I'm going to do this, I'm going to work out the numbers. Clearly divided by 1 doesn't do anything. Times by 100 is the same thing as times by 10 to the second. Now I'm doing 10 to the negative second times 10 to the second, so it's 10 to the negative second plus 2, or 10 to the 0, which is 1. So those cancel. So this is going to be 2.7%. Now, I've got this thing I want to say first, and we're going to write it, and then we're going to prove it, because it sounds really weird. All right. So for a weak acid, the percent dissociation increases as the acid becomes more dilute. All right, I want you to write that down. Turn the computer off, or the video. Think about why this might be true. Just like try and process it for a second, and then come back and let's do an example where I prove this. We're going to work through example 1410. This is written in your supplemental notes. Calculate the percent dissociation of acetic acid, Ka, which has 1.8 times 10 to the negative fifth, so that's the equilibrium constant, in each of the following solutions. So we've got a 1.00 molar solution of acetic acid and a 0.1 molar concentration. So we can tell that this is more dilute. Okay. So let's go for our answers. So part A. We know that it's an acid, so out of our major species, the acid is going to be the one that is giving up the hydrogen ion, plus this Ka is much larger than the Ka of water. So I'm just going to write out my whole equilibrium equation for acetic acid. If you're ever confused about which hydrogen is going to pop off, generally they're going to write it so that the hydrogen that pops off is written on its own. So notice how it doesn't say H4 as a total. This H is written by itself, which tells you that that's the one that's going to go away. We also have the Ka expression, so that's going to be the concentration of hydrogen ions times the concentration of acetate ions divided by the concentration of acetic acid at equilibrium. We know that Ka is 1.8. So let's write this over here. So 1.8 times 10 to the negative 5 equals the concentration of hydrogen ions times the concentration of acetate ions, all divided by the concentration of acetic acid. Now, you could do your ice charts and everything. I'm going to skip a few steps now since we've done this quite a few times. We know that this is going to be X, this is going to be X because I have one of each of these. And I know that because it's a weak acid, this is basically going to be its initial concentration. So this is going to be X squared over 1.00. It's approximate, right? Because this should be 1.00 minus X. But because X is so small, because it's a weak acid, we're going to ignore it down here because it makes your math a little simpler. So divided by 1 doesn't do anything. So I'm going to square root the both sides. Woo, that was terrible English. I'm very sorry. So I've got 4.2 times 10 to the negative 3, when I do this in the calculator, equals X, which is equal to my hydrogen ion concentration. Cool. Now I did all this work. What was I trying to solve? Let's go back. The percent dissociation. I have not found that yet. So the percent dissociation is going to be the concentration of hydrogen ions, because that's how much dissociated, divided by the concentration of HC2H3O initially, times 100%. So this will be 4.2 times 10 to the negative third, divided by 1.00 times 100. Remember, this times 100 is really 10 to the second. So then I can add these up. Divided by 1 won't do anything. So I'm going to add things that I multiply. So negative 3 plus 2 would be negative 1. So this is 0.42%. That's how much dissociated. Not even a full percent of what you put in. This is a very weak acid. So let's do part B. Let's do this for the lower concentration and see how it changes our percent dissociation. So part B, we've got the same equation, we've got the same Ka, it's just now our Ka has a different initial concentration. 1.8 times 10 to the negative fifth approximately equals our new X squared divided by 0.100 times, oops, that's just Ka, there we go. So here's our new Ka. To get rid of this 0.10, then I have to times by 0.100 on both sides. Those go away. This is like dividing by 10 again, right? Because 0.1 is the same as 1/10, and 1/10 is the same as 10 to the negative 1. So this becomes 10 to the negative 6. I'm going to take the square root of both sides. We can already tell that my 10 is going to be half of that, 10 to the negative 3. Square root of 1.8 is 1.3. So this is your concentration of H+. I can now do my new percent dissociation. So that's going to be my 1.3 times 10 to the negative 3 divided by the initial concentration for this guy, which was 0.100 times 100%. I'm going to rewrite all of this in terms of tens. So this is 10 to the negative 1. This is 10 to the second. So this is 1.3 times 10 to the negative 3 plus 2, because the 2 is being multiplied, minus my negative 1. And all of this is percent. Negative 3 plus 2 is negative 1. Minus is plus. So negative 3 plus 2 is negative 1. Plus 1 is 0. So this is 1.3%. This disassociated more than 1%. This didn't even make it to 1%. So you can see that for a weak acid, the percent dissociation increases as the acid becomes more dilute. So let's think about why that is. If you keep in mind, over here I'm dividing by your initial amount. So when you divide by a smaller number, that's going to make a bigger number. So even though in the dilute solution, we made less H+. So here is our H+ for our initial concentration. Here's our H+ for our second concentration. And you can see I made more H+ here. But because I had more to start with, even though I made more, it didn't disassociate out of how much you have. So it still disassociated a smaller percent of your total. Overall, this made more H+, but it had more it could come from. This made less H+, but it had less of what it started from, so it was a larger percent of the initial amount. So let that kind of marinate for a bit. You might need to think about that for a few minutes. Go over this problem just to get this concept in your head. I might go over this problem a few times if I were you. We're going to continue for problem 1411. So in problem 1411, lactic acid, which is HC3H5O3, we can see that this is the hydrogen, by the way, that's going to pop off when it becomes an acid that dissociates. This is a chemical that accumulates in the muscle tissue during exertion. If you guys remember from biology, this happens during anaerobic respiration. You make lactic acid, so when you've used up all the oxygen, then you're going to start making lactic acid. So it's when you really work your muscles really hard. So you start going to anaerobic respiration. This is why you stretch at the end of working out, to get that lactic acid moving so it doesn't cause cramps. Anywho, in a 0.100 molarity aqueous solution, lactic acid is 3.7% dissociated. Calculate the Ka for this acid. All right, so for this, I want to just write out some stuff just to get my mind going. So this is what I want to solve for. Ka equals, and then I have to do my equilibrium formula for this acid. So hydrogen ions times acetate ions divided by acetic acid. Now, since this is a weak acid, I know that this guy is going to be 0.100, because it's going to take my initial concentration, and it's technically minus 0, but we're going to ignore it because that's so small it doesn't really change your overall math. It becomes insignificant in our calculations. So this is what we need to solve for, the H+. Whatever this is going to be the same as your acetate ions because it's a 1-to-1 ratio. We have another equation that uses our H+, and that's the percent dissociation. So that's going to be H+ concentration divided by acetic acid concentration initially times 100%. And we have everything here except for H+, so when you only have one variable, it's very easy to do those calculations. So if I were to plug in what I know I have 3.7 equals H+ divided by 0.100 times 100. If I rewrite this with my tens, this becomes 10 to the negative 1. This becomes 10 to the second. So this is 3.7 equals H+ times 10 to the second. I'm starting with this on top. And then this is on the bottom, so it's minus, because this is dividing, negative 1. So it's minus your exponent when it's on the bottom. So this is H+ times 10 to the third. Now if I want to get rid of this, I have to divide by 10 to the third on both sides. So this becomes 3.7 times 10 to the negative third is your hydrogen ion concentration. So now that I know my hydrogen ion concentration, I can plug that in for both of these and find my Ka. If it's the same thing, it's just 3.7 times 10 to the negative third squared all over 0.100. 3.7 squared is going to be 13.69. 10 to the negative 3 squared is 10 to the negative 6. And then I'm dividing by 0.100, but I'm going to put that in a 10 form to make my math easier, 10 to the negative 1. To put this top one, I'm going to put it both in proper scientific notation on the top, and I'm going to get my sig figs right, because I only get to keep 2 sig figs. So I know my decimal has to be here. So I know it's 1 and 4. I'm sorry, I know it's these 2 digits. The 6 bumps the 3 up to 4. So I know that front number is going to be 1.4. Now, because this is a negative exponent, my decimal, really, if I were writing out, would be 6 spots that way. So since it's really 6 spots that way, once I move it over 1 to the left, from here, it's only 5 spots over. So this is now 10 to the negative 5th. I've divided by 10 to the negative 1, so when you divide, you subtract my negative 1 exponent. So Ka is 1.4 times 10 to the, this becomes plus, so negative 5 plus 1, negative 4.